Okay, so today we're going to learn a little bit about rivers, surface water, and some flooding. So, of course, the class here is focusing on the hazards. So, we do want to focus on some flooding and kind of learn about some properties, factors, things that influence flooding events. But just like some of the other kind of aspects like volcanoes and earthquakes, we do need a little background. So we have to know kind of the pieces and parts of rivers, how rivers move, and some terminology before we can kind of get into the nitty gritty of the flooding hazards. So that's kind of what we're going to do. And like I said, it's similar to what we've done before. So we're going to go through a quick little introduction on rivers, and then we'll move into the flooding hazards, and then kind of what can we do about it, and all that kind of good stuff. So what we want to talk about just initially is, we haven't really done this in this class, kind of the water cycle. Where's all the water at? We know there's lots of water in the ocean basins. And of course, there's other water on our planet. We have, like you can see in this image here, we have some, frozen water, ice caps, glaciers. We have lake streams, groundwater, and atmosphere. And of course, the majority is in the oceans. But if we just want to take away the oceans, because we just don't care about those at the moment, we want to just look at freshwater stuff. This is where all the fresh water is. And so most of it is in ice sheets and glaciers, at least at this point in time. There's some groundwater, and then there's a lot actually. And we'll talk about groundwater and a little bit about how we have some hazards related to groundwater. But for today, we want to look kind of at these river waters. And it seems like there's much more surface water like rivers and lakes because we can visually see them. The groundwater we can't because it's under the surface of the earth. So it's a small portion when we talk about, the overall amount of fresh water available to us. And of course, the hydrologic cycle is just this understanding as there's this kind of cycle sequence going on where in the ocean basins we're evaporating. That's where most of the water is. We evaporate that into the atmosphere. It gets moved along by winds and things like that. And as it moves inland and there's some temperature changes in the air, we can condense that water into liquid, and then it falls, hits the ground. And once it hits the ground, it does kind of two things. It's either going to run along the surface or it's going to sink into the ground. So if it sinks into the ground, that's our groundwater. And as it runs along the surface, it's going to find these streams and rivers and funnel into them. And then that's going to allow us to have our streams that flow along the surface. That's kind of the basic idea of the hydrologic cycle. So what are rivers? And so it's some, flowing fresh water body that's flowing into another kind of what we call base level. So the ultimate base level is in the oceans, right? So the water comes from the oceans mostly, falls on the land, hits the land surface, and is actually flowing back toward the oceans. That's kind of the cycle, right? And gravity is the driver here. So it goes inland, it goes up in elevation, hits the ground, it's high, and it flows down to the low elevations. Now, certainly it can flow into a lake and just end up there. That would be the base level of that river. And ultimately, like I said, rivers are attempting to get to the ocean, and that is another base level. And that plays a role in how rivers move and flow, right? So if we have a very high elevation starting point, we can move that water pretty quickly. If we have a low elevation starting point, the difference in the starting point and the base level might not be very extreme. And so we call that the gradient, and I'll introduce that in just a second, but it's basically steepness. How steep is the slope there? So steeper might give us faster flow, and not so steep give us a more gentle flow. But here's some other aspects of rivers. Of course, we use them, they're important. And there are stages in river development. And so when we look at a river system, we have a young part of the stream, and that's kind of what we're going to call the headwaters, the ones that are up in the mountains. And then as it moves down toward its final base level, we get a maturing of the stream, we get old streams. Potentially, we can rejuvenate streams, which means that we can take that kind of old shape that's developed and make it look more youthful again. And so, but each river has a typical setup, and we'll kind of go through some of the parts here. And so one of the main parts we want to talk about is what's called a drainage basin. And so this is the area that collects all the water that's eventually going to flow into my river system. So here's just a few images of some drainage basins. For the Colorado River, this whole area is the drainage basin for the Colorado. The argument being that every drop of water that falls in this space will eventually make it to the Colorado. Now, it doesn't have to start that way, right? The Salt River and all that kind of good stuff down here in the valley where we are flows into the Salt River. Now, there's dams and all that other stuff that kind of make things a little weird, but eventually, or before the dams, that would get into the Colorado River. And so that's the water that's going to drain into there. And you could see like the Mississippi River, holy crapola, that's big. The argument, same thing, is that water that falls in this area will eventually make it to the Mississippi and then flow out into the Gulf of Mexico. And so we can look at things kind of like this, where here's just a fictitious river. There's some tributaries. Rain is falling up in the mountains here, and it is being funneled into this Fox River, which will eventually go to its final destination, the ocean, which is the base level. And so we've got these kind of divides that can separate drainage basins, and this is how we might look at different drainage basins. So in this diagram, kind of on the bottom right, you can see there's a ridge here, a high point. And so when rain falls, it's either going to go right or left here. And so this ridge is separating two drainage basins, right? So there's two river systems here, and then they flow into that. One of the reasons this is useful for us is we can evaluate flood potential. So if I know the drainage basin, so like big storm comes in and it's going to rain, dump a bunch of rain in the area, how much water is going to get dumped into this drainage basin, because that's going to get funneled to this river that I'm worried may flood. Because the water that's going to flow over here is going to affect this river, and the water over here is this river. It's not that all the water is going into one river, so I can then use that information to narrow down where flooding may occur and things like that. Okay. And so other terms you might hear is river basin or drainage basin or catchment area even. So those might be some other terms that you might hear when we talk about river systems. And so if we look at how rivers kind of are constructed and some parts of those, kind of broken down into these four parts here. So I mentioned the term headwaters. This is where the stream is developing. It's up in the mountains. And so we have rainfall that falls up here, hits the ground, it goes into these little canyons and areas like that. And so this is the steep part of my river system. It is also the youngest, because what's happening is as water flows into these little canyons here, it's actually eroding what we call headwardly. So it's actually eroding back into the mountains. It's growing in this area. These tend to be, we said, steep, and so that means there's a lot of erosion where things carve down into the ground, so we call that vertical erosion. So if you've been up in the mountains, a lot of times these are steep canyons, you get waterfalls and fast-moving water. This is the young part. As it moves out of the headwaters in the mountains and gets into the plains, this is where the gradient, which is the steepness of the river, changes. It goes from very high to lower. And so now I don't have as fast moving water. I don't do a lot of vertical cutting. I do more lateral cutting, which is a side to side cutting. And so I get this change in also kind of look of the river. It kind of wanders a little. Where up here it tends to be straighter. Down here it tends to what we call meander. And then we head toward the base level, and when we get to that base level, our river dumps any material that it's carrying into that base level and forms a delta. And delta is the debris, the silts, the muds, everything it's carrying, because the velocity changes, right? So constricted by a stream channel, I have some velocity, even though it's not super fast when we get down into the plains area. Still carries a lot of material. And so when it opens up and it's no longer constricted, there's a big change in velocity. And this is where we get a lot of material being dumped, and we grow these areas called deltas, kind of like the Mississippi River Delta, things like that. Those are enormous deltas, of course. All right, so I've been mentioning some terms. Let's finally define some of those. So gradient is steepness of the slope, right? So it's usually given, especially here in the US, in feet per mile. And so if something is 2 to 3 feet per mile, that just means that for every mile you go horizontally, there's a 2 to 3 foot elevation change. So that's a pretty low gradient. If you're talking 5, 6, 7, 800 feet per mile, that's a pretty steep gradient. We would see the steep gradients in the headwaters. We would see the low gradients in the kind of plains area. And of course, velocity is affected by gradient, steeper, faster, gentler, not as fast. There's also some velocity differences within the stream channel itself. And then the last term that we'll talk about, and this is related to the flooding aspect we get into, is discharge, which is the volume of water that's moving past a specific point in a given time interval. So there's time here. And so it is kind of length, width, depth kind of idea. And so we get meters per second or feet per second. So a lot of times you'll see CFS, which is cubic feet per second. So basically a box, a foot by a foot by a foot, a cube, I guess. How many of those would move past a particular point? So you go to the edge of the stream channel and you stand there and you go, okay, I'm going to count how many of these cubes go by me in 1 second. Of course, the stream has width to it and depth to it. So I go, 1001. And wow, there was 500. So it's 500 cubic feet per second. And so we can get these very large discharge amounts, which we can measure. And of course, as they go up, that's a lot of water. And the stream can only hold a certain amount. And potentially it gets to a point where it could overflow. So let me just show you a few things here, right? So I kind of talked about this already, but we see higher gradients up here, lower gradients down here. We see kind of these straighter stream channels, and we see these more meandering stream channels when we get to these lower gradients. And of course, when we have high gradients, we tend to see kind of waterfalls and fast moving water. We're carving steeper canyons and things like that. When we get to lower gradient stuff, we get into, let me go back for a second. We get into this deal here. The stream is now wandering around. The area is pretty flat. We develop some other features here, but this term given to the kind of back and forth is called meandering, a meandering river. And this is because we have these very low gradients. We still have some differences in velocities, and that is really what's driving this meandering that we see. And so if we look at where the velocities are in stream channels, if it's just a straight channel, the highest velocity is kind of in the middle toward the top because there's less friction. As we get closer to the edges, whether it's the sides or depth, there's some drag there and it slows down the velocity. But the interesting thing is what happens when we go around a curve. When we go around a curve, we move the maximum velocity around. And what tends to happen is the outside bend of every river has the highest velocity. And the inside bend here has the lowest velocity. This is what's driving this kind of back and forth movement of the stream over time, which means these streams don't stay in the same location for long periods of time. As long as we don't control them, they will grow and change, because as water comes cruising down here, it impacts this side of the river, the outside bend, and it actually erodes here, and it's going to carve into this material and remove it. On the inside, it's actually going to add material because it slows down and it drops some of the material it's carrying. And then as it keeps going and around the outside bend, it erodes out here and deposits here. So this is being carved. So this over here by C is actually moving to the left. Over here by A, my stream is actually moving to the right. and this meander will grow. It'll be more of a meander in the future, way out here and way back here. Even in this picture here, this outside bend here. And it doesn't matter if the stream's going this way or this way. It's still the outside bend, and this is the erosion part. This is the deposition part. So we want to be careful when we think about, where we want to build, and if there's ever a flood, where would we get the most erosion? Outside bends are usually bad. We don't want to build there, or unless we have some structure given to this, right? So here's the deal. Stream starts like this, but over time you can see the stream is changing. It's becoming more curvy, if you like, right? And this is due to the different velocities that we see here. We have erosion on the outside, deposition on the inside. All right, what else? So here's just some other terms. We sometimes call this outside bend the cut bank because it's being cut, and the inside the point bar where deposition is occurring. Okay, so you might hear those terminologies there. So a lot of things that are affecting, how this river is eroding and depositing, of course, is this discharge amount. And so I mentioned that. So here you can see its channel width, channel height, and the velocity. And so what I want to do is know the, how much water, how deep is it, how wide is it, and then how fast it's moving. And I can calculate a discharge rate. And so when we talk about discharges, size of the stream and its velocity make a big difference. Here's some CFS numbers, cubic feet per second. And so the Mississippi River, which is really big, is maybe 600,000 cubic feet per second. So if you're standing on the edge of the Mississippi and looking across and say 1,000, there's 600,000 1 foot by 1 foot by 1 foot, basically boxes going by you, like a basketball, I guess. Amazon, 7 million, right? So these are big numbers. These are moving a lot of water in these areas. And so when we mentioned about how streams kind of weather and erode, and so in high elevations, they cut down. Because there's such a steep gradient, we start to carve and we get these shapes, these kind of canyons and things like that. Great V shapes, high, we get slot canyons and things like that forming. When we get to these low gradient streams, now we're talking side to side weather and erosion, right? So look, this is another image that shows this is how the stream might have started. It's fairly straight. But over time, why the outside bend gets eroded and it shifts, inside gets deposited, and it starts basically to become more and more kind of curvy, if you like, meandering more and more. And actually what happens is over time, this starts to get closer and closer to the point where the river will actually break through and leave behind an old meander. And that can be filled with water, and we would call that a oxbow lake. So a stream might start out like this and end up like this. And eventually it could cut through here and abandon this part of the river, or cut through here and abandon this part. And now the course of my river has changed, and it will continue to move, side to side all over the place over geologic time. Of course, we as humans try to restrict that, but we can see that it's happened in the past, right? I can see that. And of course, if we look at buildings, you're like, here's an outside bend of a river. You don't want to be there because during a high velocity, flow, or if there's a flood, it's going to carve into that. And now, oops, you're a little too close to the river. And so I could show you a few of those. If we look at, just to illustrate the point here, I'm going to show you some Google Earth imagery. And so if we look at the Mississippi River, so we're going to kind of take a quick peek at this here. And so here's the United States, there's Mississippi River. We can kind of zoom in here and see the current course of the river is, of course, the brown here. But if I cruise around, I can see that, what's this thing here? This is an old, let me get rid of that. Okay, this is an old meander from the Mississippi. It's now a lake. It's been cut off. It's still filled with water, so we call it a lake. It's an oxbow lake. But the river used to flow up and around here, but it cut it off and abandoned it. And as I look around, I can see evidence all over the place for past courses of the river. Right here, there's a shape. Here, 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 here. They're everywhere. And now the current course, like here's another one. It's way up here. Oh, there was one way out here. This whole area here is what's called the floodplain. And so in these low gradient streams where they're broad and flat, we have meandering going on, we have side-to-side erosion going on, we have abandoning these loops and making oxbows, and we have a broad, flat floodplain because the river is moving back and forth over geologic time, and it's carving this floodplain. And so in some cases, it's in the middle of the floodplain, like we see here. But as we track it, it kind of moves to the edge of the floodplain. Now it's on the right side. This whole area to the left is a floodplain. And here is probably a little harder bedrock that it's trying to carve into. And eventually it'll widen that and the floodplain will become even wider. But the river does not stay in its course over time, unless, of course, we keep it there. But over thousands of years, the Mississippi River has wandered back and forth in this area, creating a floodplain, very fertile and all that kind of good stuff. But this is what a low gradient stream would look like. Okay, let me get this out of here for us for a sec. All right, so a few other points before we get to flooding. I'm trying to go, I need to move a little faster here, but when we have streams, they're moving material. They do it in three different ways. The velocity is either dragging, bouncing, or rolling things along the bed. That's how it's moving some material. It's got some that's what's called suspended. It kind of stays in the water column and never touches the bottom. And then there's this dissolved load, which is stuff that gets dissolved in water. And so this is the three ways that streams move material. And so because it's moving material, when we flood, that material can be transported into areas, and some of that deposition of that material is problematic for our flooding events. But this is just how streams move in these three different kind of areas of our stream kind of column here. The heavy stuff along the bottom, the lighter stuff kind of in the middle, and there is a dissolved load also. And so when we get deposition, a lot of times it's from big flood events. And so when we look at the rock record, rounded pieces here are good indications of water movement, and big pieces tend to mean high velocity, lots of water moving very quickly, and so we can get kind of flooding related to that. So we can look at this and maybe talk about these are old flood deposits. When we look at the geologic record, rivers may still be here, may not be here, because they may have migrated over time, or they could have stopped flowing in this direction, depending on how old these deposits are. The term alluvium you might hear is material that's being moved from a river system. And of course, we deposit that when the river typically changes velocity. So that's certainly at our delta at the very end, but it's also at points where we overtop the banks and flood out into a floodplain. We get a velocity change and we dump a lot of material that way. All right, what else? So these are some features, right? High velocity, these are the high gradients. We get these types of features. Low velocity, right? We have stream channel deposits. We kind of get these meandering things. Levees are something we want to mention because, of course, they're related to flood events. And so naturally, when a river overtops its banks, it deposits the heaviest stuff here. And that's because when it first comes over the top, it has some energy, but then as soon as it comes out here, it loses energy. And so then it deposits the big stuff, and then you get a natural levee built up over multiple floods. Of course, we build artificial levees to help kind of keep flooding from occurring, but this is what a levee is when we talk about levee systems and, kind of using that to help with flood events. Here's the floodplain we kind of mentioned, if it wasn't clear when I was kind of jumping around there. In our kind of low gradient streams, we develop floodplains, and that is because we talk about the stream is moving around in this floodplain. Normally, it's constricted to the channel, but when we get these big events, we can flood and fill this floodplain with water and sediment. And what else I got for you? And of course, rivers move around and cut, and so they can cut down into sediment, they can meander back and forth. And we get these kind of what are called terraces, which tell us that there's some elevation change causing things to cut down into its own deposits. We get these meanders in Oxbow Lake. So here's just another diagram. Here's a great one over here on the right. You can see that this recently was cut off, and now the river's going this way, but it did flow way around here. Cut off. Eventually this will silt in. There's our Oxbow. There's another Oxbow Lake. This one's going to fail. So the changing river systems in these low gradient streams is why we get this kind of meandering look that we get. And then finally, we have our deltas. That's kind of where we dump all the material at the end, and this is kind of how that looks. Just another part of our stream system. Okay, holy cow, let's talk about flooding. All right, some terms that we might talk about when we talk about flooding. So discharge is certainly something we want to talk about because that's the amount of water. And so when we have high discharge rates, that's an indication there might be a flood. We're going to look at some hydrographs. What's a hydrograph? Well, that's this thing here to the right. And it is plotting discharge, so this cubic feet per second amount of water over time, and the time to the right here. And so what this would illustrate would be a flood event. So it's showing that at some time, this is our normal discharge on our river. It's kind of just hanging out. Everybody's happy. And then there's this big increase that's very quick, and then it peaks, and then it lowers down back to this normal level. And so this lag time here is related to how long it takes for an event, like let's say heavy rainfall, to impact our river. And what we'll see is the different types of floods that we get are going to change the shape of my hydrograph. Okay, and so we'll talk about flood stages, and we'll also talk about what's called recurrence interval. So recurrence interval is something we can kind of calculate when we have some data from our stream and tell you the average time between certain flood events. And of course, that's useful. Now we're talking about flooding. We want to warn people. We want to have some knowledge about how often does this river flood? Does it flood every year? But how about the big ones? Does it flood really huge every year, or does it have small floods and the big floods only come every 10 years? Well, we want to know that, and we can estimate that with a recurrence interval based on some knowledge we have of the rivers. And so when we talk about recurrence interval, we talk about how often a certain size flood would occur. And so we have 100-year floods, 50-year floods, 25-year floods. And so we can calculate those based on the history of flooding on that river. If I have that information, I can say, look, this certain size flood, well, how big? Well, a 50,000 CFS flood. 50,000 cubic feet per second flood might only occur once every 100 years. But a 5,000 CFS flood may occur every 10 years. And so this is the recurrence interval. We can calculate the probability of that happening. If we have a 100-year flood, in theory, in every year you have a 1% chance of it happening. And of course, the 25-year flood, about a 4% chance of happening, right? So, and look, these are predictions. They're not always accurate. In theory, I could get a 100-year flood one year, and the next year I could get another 100-year flood. On average, they should happen one every 100 years. But given the way nature works and how things are, that's not always the case. But it is a prediction that can be used, right? And so here's the kind of the math to calculate that. We'll kind of do this in the lab here. But basically, if I have the magnitudes of the floods, and I have some records going back in time. Like I've collected, data on this river for 50 years. The more data I've collected, the more accurately I can predict a recurrence interval. And then we can always do the probability too, but we'll do more of this in the lab for this topic. Okay. The two types of floods that we're going to categorize here are called either a flash flood or a regional flood. And so the flash flood you've probably heard of if you live in Arizona, because these are floods that kind of happen fast and furious. We kind of call them upstream floods. And so they're typically forming in the upper portion of the drainage basin, but climate and other things can play a role in whether you get a flash flood or you get a regional flood. But what we want to say about flash floods is that they're fast and they're short, and they usually cause some damage very quickly and then they go away. And so we get these heavy rainfalls that overtop streams quickly or run down streams, and they do some damage and then they're done. And so if we look at kind of how, flash floods work, heavy rainfall, short period of time, all that water flows into my river system. It overtops its banks, or here in Arizona, we get dry riverbeds that automatically now become, wet, and there's pushing a lot of material through, and they can cause damage to structures like, bridges and things like that. And so we get those here in Arizona for sure. On the main page, there's actually an image of a flood that occurred in Page, Arizona, illustrating a flash flood event. And even here in Arizona, we kind of had something happen which you don't really expect, but the Mill Avenue Bridge. Now, of course, if you're here in Arizona, the Mill Avenue Bridge is a bridge that goes over the Salt River. But now today, the Salt River is a lake because we've made a little artificial lake there. But it is still a river, but it doesn't really flow anymore because we dammed the water upstream. But back in 1993, when the Mill Avenue Bridge was being built, there was so much water, heavy rainfall that occurred throughout the state that they had to release a ton of water from the dams, and that flowed down the Salt River. And at the time, they were building the bridge, the Mill Avenue Bridge. And
two spans of the Mill Avenue Bridge, still under construction, was shown to millions of viewers across the country.
We had some of this going on. And so it took out the bridge because, of course, the bridge wasn't completed. But, the high velocity of the water that pushed through caused, a flood event. And this was the damage that occurred. The other thing to think about when we could talk about this particular event that happened in 1993 was that, let's see if I can get it for you. So we got this going on here. So what happened was the water flows down the stream, and they're not prepared for it, and there's a landfill. Okay, and so where did they put the landfill? Well, remember, these streams are meandering. They're moving back and forth. And so on the outside bend of the river, someone decided a landfill should be there. And we know that erosion is occurring on the outside bend of a river. And so, unfortunately, it ate into that outside bend of the river, and yucky. So that was not very good. Right? So, but some of this information that you now have is useful, that you can kind of understand why these flash flood events are something to be concerned about. And, when we build and do stuff, we have to be aware of river systems and how they behave. And so flash flooding, this is the kind of big events that we see that happen, usually related to heavy rainfall. But we can get some other events that cause flash floods. And sometimes that's related to either a dam or a levee failure. And here's just some examples of some dam failures or levee system failures. And so there was a couple dams that happened where they failed. And of course, you have to imagine you're holding back this huge amount of water. and there's this collapse of the dam. That water is instantly pushed down into the river, which obviously is way more than it can handle, and it moves downstream at a high rate of speed. Usually, then there's some town or community kind of at the base of where this kind of stream empties out into, and of course, that's where the damage is done. So, the St. Francis Dam happened in California. There was this one happened way back in 1889. So, these are just some examples that we could look at when we talk about dam failures. Here's the St. Francis Dam collapse. You can read a little bit more about it here. But one of the things we want to be aware of when we build dams is rock type. And so as you look at kind of this diagram of the river, of the dam and the rocks that were around it, there was some old faulting here and some rocks that really weren't that strong. And so probably not the best place to build the dam. So another thing to, take into account is, we got to look at geology when we're building these structures so we don't have these failures that can occur. Now, usually we do a really good job, but not always. And this was kind of before there was more kind of studies done before some dams were built and put in. There was this other kind of failure that led to a flood, right? And this is a unique one here where this was actually a landslide-induced flood, but still rainwater was really the kind of big cause here. And so it over kind of saturated the soil above a reservoir. And then there was a big landslide that basically splashed into the reservoir, and the water created a huge wave that overtopped the dam, came down into the village below, and did a lot of damage for that town. And so that's kind of our flash floods, right? So usually driven by these high, fast, and furious rain events, but not always, right? We can have dam and levee failures that do that. They come in quick, they end pretty quickly, and they're a short duration event. When we talk about regional flooding, how we're talking about these big, huge, covering large area floods. These are slow. They take a lot of time for the streams to, get all the water into the system. Then they potentially overtop their banks. They flood a huge area, and it tends to last for a longer period of time. Now, there's exceptions to every rule, and a lot of times there's a little bit of overlap here, but flash floods are usually, there's no big floodplains there. It's the material moving down the stream itself and then emptying into a place or overtopping quickly. Whereas these regional floods are these big, kind of the Mississippi River flooding, right? These are huge systems with a lot of water being brought into the main river system and big floodplains. If we get enough water, we can overtop the levees, and then the water floods out into the floodplain and hangs out for a while. Doesn't go away very quickly, and that's kind of the big issue that we have for that. And so if we look at a hydrograph, we would get these different shapes based on the type of river and the type of flooding. A flash flood comes in fast and ends fast, and a regional flood lasts a lot longer when we see these kind of big events like this. And these are common, when we look at flooding throughout the U.S. So this is a map, the colors representing presidential declarations related to flooding. Red, 4 or more, like Arizona, we've had our share, right? California, in the Mississippi River area for sure. So there's been lots of times where there's been large flood events that occurred. And most of these, we'd argue, are regional because they devastate a larger area, and that would be something that we would get a presidential declaration for. But you can also have some issues related to these flash flood events, okay? All right, so what happens when we get flooding? Well, we're going to go through and just list all these things, right? So certainly the impact of the water itself, so whether that's striking objects or people or things like that, is going to cause some damage. So the current, the debris, and the sediment, right? These are what's damaging structures and potentially people, right? So homes, buildings, bridges, roadways, all that kind of stuff. These are the kind of things that we would see when we talk about big flood events like this. So the higher the velocities, the bigger the discharge, right? The more material they can carry, the more damage they can potentially do. And so when you have these high velocity, big discharge areas, they're moving material, but they're also potentially eroding stuff. So they can undercut bridges, roads. There was some flooding in Yellowstone recently where they, took out roadways. This high velocity, high energy, right, has the power to weather and erode like that. And so certainly we get pollution, we get disease, we get homelessness. These are all things that are secondary kind of effects once the flood takes over. So we have the initial water doing damage because it's got strength and power and velocity. But then, of course, once it's there, especially in these regional events, the water can hang out for a while. And so then it's mixing with, all the pollutants that are out there. And so then that has a problem with access to clean water, people actually having access to leave their homes if they're trapped in there, and then, waterborne diseases and all this kind of stuff are other factors to consider. Why do we get these floods and damage? So there's some factors we can talk about. So certainly how we're using the floodplain. If we're allowing everyone to build their condominiums and homes in floodplains, then that's going to affect the amount of damage that would occur in a regional flood. So if we restrict building in floodplains, we can eliminate some of the problem, basically by removing the people. And certainly how fast the water's moving and how deep it is going to be something that affects the amount of damage that would occur. How fast it comes in. Do I have warning? Right? If it's a flash flood and I wasn't even expecting it, I can't get out of the way and potentially there's more damage. If I know one's coming and I've warned and I've packed up my goods and gotten out of there, then I can reduce some of the damage. Seasonal, we know here in Arizona, monsoons come seasonally and they drive some of the flash floods that we get here. And in other areas where we have, seasons with high rainfall, the potential for regional flooding is increased. How much sediment is deposited? So especially with regional, but not always, these high velocity, big streams move a lot of sediment. And once they're done, they leave a lot of that behind. And sometimes that can be more damaging than the water itself. In some of these big regional floods, you can leave 2 feet of sand and silt and mud behind. And so if your house gets flooded, you have water damage, the water recedes, and now you have 2 feet of mud in my house. So that's going to impact some of the issues we have with damage. And then, of course, how well we can predict. The better we can predict and warn and get people out, then the better off we'll be to be able to reduce some of the damage. And so we also see some issues with changing the land can, either increase or decrease the amount of flooding. And a lot of times when we build big cities or lots of infrastructure, we're coating the ground with concrete, which doesn't allow water to sink into the ground. Instead, it all flows on the surface, which means it all goes in the streams. Where naturally, some of that water would sink into the ground and not make it to my stream. Less water in my stream, less chance for flooding. But if I've modified that area, I can push more water to the river and less in the ground, and then I have some issues with that. And so that's kind of an urban effect. We have a farming effect, right, where we take out the trees and we start to farm. Well, now we don't have the trees to take up the moisture, and so we get a lot of more erosion, and sediment gets into the stream, and that affects how the stream moves and behaves, and I can make a deeper channel not so deep by dumping a lot of sediment in there, so now it floods easier. And so this is some issues we get with changing how the land is. And here's the kind of the urbanization issue, where when we urbanize, we make the floods bigger and they come faster. And that's related to this idea that when the water hits the ground here, it can't soak in. Where normally there's a percentage that gets soaked into the ground and doesn't get in my stream. Where here, all of it might get in my stream, which means it gets in there super fast and more of it. So lag time is less and peak is bigger. And then the other thing I wanted to point out, and this is related to that previous one, but when we look at, because I don't know if I had a good hydrograph about this, but we want to remember that if we're looking at a hydrograph, we could estimate a couple things from here. But here it's showing how, when we take away the forest and we build things, we, just like we talk about, we have a bigger flood and it happens faster. Whereas when we don't do that, we can have smaller floods because of this absorption rate. We can also look at these and argue that they also may represent the difference between a flash flood, this bigger, faster, shorter lag time event, and a regional flood. And so flash floods tend to be fast and furious. So they come quick, they peak really fast, and they leave really fast. Where regional ones build, come, and they last a lot longer. So we can use hydrographs to kind of interpret what's happening in the flood event based on the different shapes of the hydrographs. All right, and finally, how do we control this stuff? Well, we build dams. And so we build dams for a variety of reasons, but a lot of times it's to control flooding. Before the Hoover Dam was built, there was tons of flooding in the Colorado River area, especially as it traveled south toward the Gulf of California. And so building a dam can allow us to control it. So obviously we can store the water, which we like, but it also helps us control how much we let out. And then we can, help out with some flooding events. Levees, we build levees or make them taller. That can help. Or floodways, where we allow certain areas to be flooded or funneled, so we channel some of the water in different locations. And so here's kind of some examples. Hopefully they're not too cut off, but some dams, some levees built up on the side here, or some flood walls, or specific, canals that we've built to allow the water to move and go to certain locations. And then, of course, can we predict floods? Well, we kind of can. And so how do we do that? Well, our favorite thing, we map. And so we look at past floods. Where has there been flooding in the past? We look at elevations. We know lower elevation areas are more susceptible to flooding than higher elevations. Closer to the stream channel, you're more apt to get flooding. And so if we can make maps, then we can kind of warn people or give them the probability of you having a flood is higher here. We do recurrence intervals to give people an idea of how often big floods occur. We have monitors that monitor the water constantly, and so if there's a flood coming, we can kind of predict. So we want to do stuff like that. And then the other things we do, of course, is we put laws into place to try to keep people from building in areas that are flood prone. So sometimes we force people to get flood insurance. That can be a deterrent. Hey, if you want to live here, it's going to cost you. Well, okay, I don't want to live there, so I'm going to go live somewhere else where there's not as much a flood hazard. And so these regulations are designed to kind of educate people, like, hey, you're in a flood plain and this is what's going to happen. Different building codes, right? Because we know that you might be exposed to that, so your house might have to be built in a different way to withstand a flood or survive a flood. And so, here's more regulations that are trying to either restrict people, like you can't build there, you have to build a certain way, or you have to have a certain amount of money to do this, and all these kind of ways that we want to keep people out of the danger zone, basically, right? And so if we look at an area like this, we might have something that says, we've calculated that this is the 20-year flood area. Nobody can build there. So you're not allowed to build anywhere in this zone. Here's the 100-year floodplain. You can build there, but you have to build in a certain way, right? We have to have these kind of regulations that allow you to do that. And so this is one of the main ways that we're trying to reduce the amount of hazards associated with flooding. And so that's how we would kind of get people to stay out of the danger zone, right? All right, so that's going to kind of wrap up the stuff about flooding. So you got that intro about all the nuts and bolts of rivers. And then the main point, of course, is these two kind of extremes where we have flash flooding, regional flooding. Definitely a climate issue. It's also, a size issue. It's a seasonal issue that you want to kind of consider these different events, and understand how the discharge rates and the time that it takes to have these floods occur, who's impacted, and things like that. There are, like I said, 2 additional videos on the main page that show a regional flood and a flash flood, so you can look at those to hopefully kind of get your eye if you're not sure of how all this information pertains to the flooding, so you want to kind of know the difference. And yeah, there's overlap, like we talked about. Can you have a flash flood that turns into more? Yeah, okay, we can get some of that, but typically we can categorize those into those 2 groups. Okay, I'm done. If you have any questions about some of this content, please don't hesitate to contact me.